Today we discuss one important theorem related to multiplicity of roots. Okay, we write the statement of this theorem first here. Okay, for any field k, for any field k, okay, an irreducible polynomial, an irreducible polynomial px in kx, okay, px in kx is separable, okay, is separable if and only if px and its formal derivative, px and its formal derivative, okay, p dash x are relatively prime, are relatively prime for any field k. An irreducible polynomial px is separable if and only px and its formal derivative are relatively prime. We now prove this theorem. Okay, we write proof here and going to further discussion of that. Okay, let dx denote that means GCD of px and p dash x. Okay, let dx denote the GCD of px and p dash x. Okay, px and p dash x, not a problem at all. Suppose px is separable. Now suppose px is separable. Okay, then what happened? Let c be a root of px. Let c be a root of px. Okay, c be a root of px in some field containing k. In some field containing k. Okay, then what happened? Then px equal to, here x difference c multiplied by fx. Okay, for some fx belongs to this kcx. Okay, not a problem at all. Now here we write, since px is irreducible, since px is irreducible, okay, irreducible, then fx fc not equal to 0. Okay, so not a problem at all. Then fc not equal to 0. Okay, now p dash x equal to, what happened? So fx belongs to kx and obviously px is irreducible, then fc not equal to 0. Okay, now c be a root in some field containing k, that means one field containing k. Here c be a root of px. Okay, then px equal to this one. Okay, so fc not equal to 0. Okay, now we write here we evaluate this p dash x. Okay, p dash x equal to what? Here x difference c f dash x plus fx. Okay, then we write in this way, p dash c equal to 0. So here P dash C equal to what? F dash C, FC. Okay, P dash C equal to what? FC. Okay, FC not equal to 0. P dash C equal to what? FC not equal to 0. Okay, now what happened here? Hence C is not a root of dx. Okay, and where every root of dx must be a root of px. Okay, so we write it, that means dx is the gcd of px and p dash x. So here p dash c not equal to 0, so c is not a root of dx. Okay, so c is not a root of dx. Okay, then what happened? We write here, we erase our portion and going to further discussion of that. Now what happened here? We write in this way, but every root of dx, but every root of dx, okay, must be a root of px. Okay, must be a root of px. Okay, px, since what happened here? Since dx divided px, right, every root of tx must be a root of px. So since dx divided px, dx gcd, so divided px. Okay, so what happened here? Thus dx and px have no common root. Okay, thus dx and px have no common root. Okay, dx and px have no common root, so dx has no roots, so dx has no roots. Okay, therefore dx equal to 1. Therefore dx equal to 1. Not a problem at all. Now also, that means see this one, dx equal to 1 means px and p dash x are relatively prime. We find this one. Okay, so px and p dash x are relatively prime. Okay, now we write conversely. Okay, we erase this lower portion now and going to discussion of, that means, converse part. We write here conversely. Okay, then what happened? Suppose that dx equal to 1. Suppose that dx equal to 1. This one px and p dash x are relatively prime. Then this one happened. Okay, now let c be any root of px. C be any root of px. Okay, let m denote the the multiplicity of c, multiplicity of c. Okay, then what happened here? Then we write in this way, then okay, px equal to x minus c whole to the power m, here fx. Okay, where this one over kc. Okay, over kc, and c is a root of fx, and c is a root of fx. Okay, sorry, c is not a root of fx. Okay, not a root of fx. Px equal to this one, not a problem. That means c multiplicity m, and obviously in this way, and px, c is not a root of fx. Okay, not a problem at all. That means c occur m times, and c, that means m times root of px, so we write in this way. Okay, now now p dash x we evaluate. Now p dash x equal to what? In this way, m x minus c whole to the power m minus 1 fx, and here plus x minus c whole to the power m f dash x. Okay, then what happened here? Then x minus c whole to the power m minus 1 common, then here m fx plus x minus c f dash x. Okay, not a problem at all. Then what happened? We write in this way, we erase our portion and going to further discussion of that. Okay, we write here, that means in this way we write here, thus x minus c whole to the power m minus 1 is common factor of, is a common factor of p dash x. Okay, and px also, not a problem at all. So what happened here? Then hence x minus c whole to the power m minus 1 divided dx. Okay, dx equal to gcd of this one. Then what happened? Since dx equal to 1, so m equal to 1. Okay, so what happened? So we, that means right here, consequently m equal to 1 means px has no repeated root. Px has no repeated root. Understood? That means we prove this theorem also. That means px and its formal derivative are relatively prime, then an irreducible polynomial px is separable. Okay, not a problem at all. Px be separable, we also prove this one easily. Okay, I think all are understand this one clearly. Okay, c be a root of px, so here px be separable. Okay, in that means one distinct root here occur. Okay, not a problem at all, and obviously not repeated time occurs this one, so px be separable. Okay, Now we also discuss another theorem, okay, related to that topics. We write this statement of this theorem now, okay. We erase that portion and we're going to discuss on the statement of this theorem now. We write here theorem. For any field K, okay, an irreducible polynomial, okay, px in kx is separable if and only if p dash x not equal to 0, okay. That means we have to prove this one now. P dash x not equal to 0 if an irreducible polynomial be separable, okay. We prove this theorem now, okay. First we also see that px and p dash x, that means are relatively prime, okay. Now we also write this one, p dash x not equal to 0 happen. So in this way, let tx be the GCD of px and p dash x, okay, not a problem at all. Then what happened here, we write suppose px be separable, suppose px be separable, okay. Then what happened here, then we write in this way also, then if p dash x equal to 0, if p dash x equal to 0, we take this one, okay. Then dx equal to what, dx equal to px not equal to 1, okay. That means if p dash x equal to 0, then dx equal to what, that means dx also divide this one p dash x and px. Now we write this one equal to px, okay, not a problem at all. So this one not equal to 1 and this one, that means here we write contradiction. Why we, that means this, from this theorem we know about that px and p dash x are relatively prime. If p dash x is 0, then we write dx equal to px, and no, this one is not equal to 1 and this one contradiction, okay, not a problem at all. Now converse part, okay, that means this implies if dx equal to 1, then p dash x not equal to 0. This implies what, this implies if dx and dx equal to 1, then p dash x not equal to 0, okay, not a problem at all. Now we also erase this upper portion and going to be discussion of converse part, okay. So one polynomial is separable if polynomial and its derivative have, that means are obviously relatively prime, okay. And now we also discuss polynomial is separable if p dash x, that means derivative of this polynomial is not equal to 0, okay. Now we discuss this one converse part. We write here conversely, okay. Conversely, here suppose p dash x not equal to 0. We take this one, since p is irreducible, px is irreducible, then what happened? Then we write the only common divisor of px, the only common divisor of px and p dash x, okay, are 1 and px are 1, okay, and px also, and px also. Now since what happened, since degree of, since 1 less than equal to degree of p dash x less than degree of px, okay, so what happened, 1 is the common divisor of px and p dash x, not a problem at all. Now hence what happened, hence dx equal to 1, okay, thus what happened, thus px is separable, okay, that means px and p dash x have one common divisor, that means no common root, okay, so p dash can't contain multiplicity of any root, okay, so obviously px is separable, okay, that means px have one root and so px is separable, so not a problem at all. We also prove this two theorem easily, okay, all are understand this one clearly and properly. I think all are understand these topics, so today I'll stop here. If you get this type of video, please click on like option and please follow my channel and obviously see this video regularly and subscribe this channel, okay, so today I stop here. Thank you.